Right, so that's correct, and the nice thing is that these are basically equivalent. Like you can go from one form to the other, and this is in fact a very common thing that happens in all like zk star proving systems. Specifically, like if you have 2 to the m different evaluation points, there is a unique degree 2 to the m minus 1 polynomial that will evaluate to all of these evaluations at these indices. There's many polynomials of degree 2 to the m that will evaluate to this, but there's a unique degree 2 to the m minus 1 polynomial. And so you can move between the evaluation form of this polynomial and the coefficient form using FFTs. Like it's an n log n operation to go from these guys to each other. But yeah, does that make sense? The evaluations are the polynomial in a sense. Okay, great. So actually, this is actually a way of basically going from evaluations to like a coefficient like representation of a polynomial. In this case, it's just multilinear. Okay, let's keep going. So this thing, essentially this polynomial here, so one thing I didn't explain is like e sub I is the bits. It's the binary breakdown of e. And we're going to be using Vitalik's notation where essentially like this is the most significant bit. So what that means is like 0 is zero is not useful. Like 2 represented in normal binary is like 1, 0, but instead we're going to be doing 0 to 1. In the same way, like 11 is 1, 0, 1, 1, but in this format we're going to like basically reverse it. It's going to go 1, 1, 0, 1. So this is equal to 1, 2, 4, 8. Does that make sense? I'm going to stick with that notation. Okay. All right. So what this thing is doing here essentially is like this product, and this is something that each of you guys should like, verify on your own. This product will only equal, this product will only equal 1 if x sub I is equal to the binary decomposition of e at every single bit. Otherwise, this thing is going to evaluate to 0 at some point.
Why? Can you explain why?
Yeah. Wait, let me make sure I wrote this down correctly.
So you're just summing the coefficients of z here. Is that what's happening here?
No. This is evaluations.
Evaluations. Oh, because e is your like query point.
Sure, yeah.
Oh, sorry, x is your query point.
Yes.
Okay, right.
E is like just all the different evaluations that we have access, or like, sorry, E is the domain of evaluations that we have access to.
Right, okay. And then only at the point where x equals e will that big product be 1. Everywhere else will be 0.
Yeah.
And so you just get that value of z. Okay, right.
So let's go through this with an example.
I see, so that's what this thing on the right is.
Huh?
So that becomes this thing on the right, like that big matrix on the right. I see.
Oh, what, this thing?
Yeah.
Yes, exactly.
Okay.
So, let's go through an example here. So, like, when you have, let's look at the specific term for, like in this sum, let's look at like 11, for example. So we have like z of 11. And then the specific thing we have here is like times pi of, it's going to be, okay, we're actually just going to write this out completely. We're going to like expand the product. So 11, when you convert it to binary, is, again, in the most significant bit notation, is 1, 1, 0, 1. So what we're going to have here is like, going to have a product of like, okay, x0 times 1, and then x, or we need the times 1, oh, sorry, x0, x1, and x3. Also times 1, or sorry, 1 minus x2 times x3. So I guess we can break this down further, or like we can actually go through each index. So at I equals 0, what is the 0th bit of this number?
1.
It's 1. So in that case, we plug in 1 in both of these things. So because this is 1, this term all cancels out, right? So we just are left with x0 times 1. Great. Okay, same thing happens for x1, right? The first bit here is 1.
Why?
So this term cancels out, we just have this. Now we get to our first interesting one, 0. Okay, so with 0, now e sub I here, in this case we're doing like I equals 2, so e sub I is going to be 0, right? So this term is going to go away. And instead we're left with this thing being 1, because it's 1 minus 0, and it's 1 minus x sub 2, so we're just left with this term. Does that make sense to people?
Yeah.
Okay, the really cool thing about this now is that, like, only when x sub 0 equals 1, x sub 2 equals 1, this equals x sub 2 equals 0, and x sub 3 equals 1, is this not going to be equal to 0. At least when we're evaluating over each of these on binary. Do people believe this? This is like very important because it's going to be very relevant to like when we get to the tensor product stuff. The cool thing is like this formula in general basically does this for all different indices that you might have. Like from 0 to 2 to the n minus 1, this thing is only going to be equal to 1 when x is equal to e, which is sort of why we usually denote it as this. By the way, this tilde here means it's a multilinear polynomial. That's also why I have a tilde here.
Question,
Yeah.
why 1 minus x2 can't be 0?
So like, basically like, if x2 is ever 1, then this term is going to equal 0, and then everything is going to equal 0, right? So for this individual term to not equal 0, then x2 has to be 0. However, that also, the same kind of logic holds for every single one of these other guys. If this is 0, then the whole thing is going to be 0. If this is 0, the whole thing is going to be 0. If this is 1, the whole thing is going to be 0, etc., etc. So the only case on which every single one of these becomes 1 when you're evaluating on these being binary is when this is 1, 1, 0, 1. Does that make sense? Does this register for everybody? Wonderful. Okay. So this is a multilinear extension. Vitalik didn't explain this at all. I guess he basically just sort of, I think, shrugged this away by saying like, with the tensor products, what you're doing is a partial evaluation, which is like wholly unsatisfying. But I guess maybe he just didn't feel like going into it. Okay, so that brings us to this wonderful grid. So what's going on here, which is also not super well explained in the blog post, is that basically you take your multilinear polynomial. In this case, we have 16 evaluations, the digits of pi, and what you do is essentially you arrange them in like a grid, where you take the 0th evaluation, like this polynomial at 0, which again in multilinear form is 0, 0, 0, 0, and that outputs 3. And then at 1, 1, 0, 0, 0, it's 1, etc., 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 etc. Does this part make sense to people? Like, essentially what we've done here is we've taken 16 evaluations of the polynomial, and we've converted it into a multilinear polynomial using this setup, basically. And now we have this guy. Stay there for a second.
So like those numbers are just examples. It's like 3, 1, 4, 1. It's like just examples.
He is committing to this polynomial, is the way of thinking about it. He's defined this pi polynomial.
Yeah.
And there's 16 evaluation points. And
How are the coordinates mapping?
Huh?
How are the coordinates mapping?
So basically, like, let's say like the original polynomial here was like 0, 1. Like you evaluate at, basically it's like the index of pi. It's like what our polynomial is doing. So let's see, the original like univariate polynomial was z, and z of 0 is 3, z of 1 is 1, z of 2 is 4, z of 3 is 1, z of 4 is 5.
No, I'm asking about the four-dimensional coordinate.
Right. So what you do then essentially is you take like its index and you just convert it to binary. So in this case, like 1 in this is most significant bit binary. So this is 1, 0, 0, 0. Let's do a better example. So like this one here. So this is the 7th index, right? This is going to be 1, comma 1. Yeah, go.
1, 1, 1, 0.
Exactly. Yeah. And then what about this one?
0, 0, 0, 1.
Yeah. Is that correct? Yeah, that's correct. Cool. Wait, no, this is not correct.
No, I guess with that 7, it's 1 minus. Okay.
Yeah. So this is supposed to be 7. That's supposed to be 6. So let's do it again.
0, 1, 1, 0.
0, 1, 1, 0. What's this one?
1, 1, 1, 0.
Yeah. So you just convert the index into binary form, and also we're 0 indexing. Sorry, that's my bad. Does that make sense to everybody? I guess the one thing you missed, Richard, is that essentially, like for this polynomial, we're just converting it. We're basically making it into a multilinear polynomial, where like, yeah, you can think of it as basically being like the original polynomial we had for pi is like z of 0 is 3, z of 1 is 1, z of 2 is 4, etc., etc. And now we're just moving that into a multilinear basis where now it's like you're converting that original index into a binary representation and evaluating your multilinear polynomial at that, which again is done using like this formulation called a multilinear extension. Okay. So that brings us to these weird ass tensor products that this guy dropped on us. So what's the deal there? Well, what the deal is that essentially what you're doing is you're just evaluating this function. Like, what's going on here is like, you're basically plugging in R1, R2, R3, R4 into this formula, essentially. And as a result, like, because this is literally how we define the polynomial, if you plug it into there, like, the output of this polynomial at R1, R2, R3, R4 is gonna be just the sum of all these different things. And so if we write it out here, like the specific like row and column products, like what they break down to is essentially like the top corner, when you do both like the row dot product and the column dot product, you have this thing, this thing, this thing, and this thing at the corners, and then we can fill in everything in between if people think that's a useful exercise. But like essentially like everything in this row is gonna have a 1 minus R3, 1 minus R4 term in it. Everything in this row is gonna have like an R3, R4 term in it, and then this one is gonna be like 1 minus R3 times R4, and then R3 times 1 minus R4, or something. So that's why essentially like this tensor product, when you do both like the column and the row at the same time, is gonna actually yield an evaluation of the polynomial, which he kind of just says happens. He's like, look, it's negative 137. You're like, what the fuck? Like, how did that happen? But yeah, it's because literally this polynomial is written like this. This is like how you represent multilinear polynomials from evaluations. And so, yeah, this is an equivalent way of evaluating the polynomial at R1, R2, R3, R4. Do you want to walk through that in more detail? Like we can just go through each of these products and like show this if people want to.
Wait, so you said that we can identify a polynomial just by looking at the corners?
I don't know. I usually just lazy and only wrote the corners versions of these.
Yeah.
Like, there's a term for each of these guys.
Yeah.
Okay.
Yeah, it's just the binary representation of it.
Huh?
Like representing the binary into that multivariable polynomial.
Yeah.
So like the second one would be R1 into 1 minus R2, 1 minus R3, 1 minus R4.
Yep, exactly. And then what's this one?
Yeah, 1 minus R1, R2, 1 minus R3, 1 minus R4.
Yep, exactly.
Yeah, except as well.
Gonna get rid of these x's.
Why?
Yeah, and you just sort of like keep doing this. And in this case, like what you're gonna have is like you're gonna have like an R3, 1 minus R4 term for every single one of these because there's a 1, 0. And then here you're gonna have a 1 minus R3 times R4 term. And if you notice, this final one is gonna have like an R3, R4. So if you notice, like this is exactly the tensor product that Vitalik has in his write-up, right? It's like he just says like, okay, now multiply all your rows by 1 minus R3, 1 minus R4, and then R3, 1 minus R4, 1 minus R3, 1 R4. And this is where that's coming from. It's coming from the fact that every single row is gonna have this term in it, and that is coming from this expansion that you have here. Good erase this example.
Could you like just give one example of one evaluation at one point?
Sure. Well, like one example is like the one he gives in the post. So, like, if we have R1 is 1, R2 is 2, R3 is 3, R4 is 4. If you then do this whole thing where you multiply 3 times plugging in all those terms, 1 times plugging in all these terms, blah 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 blah.
So like what is this 3 for example at the top left? Yeah.
This 3.
Yeah.
So this 3 is what you get when you have, again, we're basically committing to a multilinear polynomial z. And in this case, z tilde of 0, 0, 0, 0 is equal to 3. That's just like what it equals at that point.
Okay.
Yeah.
That's just the characteristic of the polynomial and it's the evaluation of the polynomial and so
Yeah, and like
because in the article it doesn't define any polynomial. So
yeah.
that's the definition of the polynomial.
This like this is its evaluations at all of
Yeah.
these points
Okay.
basically. So I guess like my takeaway from this like setup here basically is like there's this really clever like basically an observation that on the rows and columns you share these terms, and so as a result you only need to communicate like square root n of like your total number of evaluations of your polynomial being n, because you can lay them out in the square, and now like you only need to communicate to the verifier like individual columns, which are all going to be like root n, as well as like obviously like the tensor product thing that you do as well. Basically you communicate a constant number of root n sized data, which is going to be a lot smaller than n.
This entire thing is just a polynomial commitment scheme.
Yeah. A kind of shitty one, honestly, but it works really well with binary fields, which is what the rest of the article goes into. Yeah.
Wait, so you plug in 3 in that equation, 1 in that equation, 4 in that, and then what do you communicate?
So, like, wait, so what do you mean? Like, what equation?
So
Like,
what happens after you have this like square of 1 minus r1s? I was
Yeah.
able to follow till there. And then what do you do with the 3? Do you plug in into that equation?
so yeah, sorry. So you take R1, R2, R3, R4. You like insert them into all these different equations. So in the Vitalik case, it's 1, 2, 3, 4,
Okay,
and then you multiply it by this evaluation.
I see.
And where that comes in is like from this equation right here, right? Where like, again, if you consider like if we're not in the binary basis, like this is 0, this is 1, this is 2, this is 3, right? So you take the evaluation of z at 0, and you multiply it times this product of like 1 minus r1, 1 minus r2, 1 minus
Why
r3.
are r1, r2, r3, r4, 1, so like 1, 2, 3, 4 again?
That's just a random point that he gave us. Like that, like this, like how this generally works is like you query this polynomial on some random, or like you're trying to open it at some random point. And the random point he picked is 1, 2, 3, 4.
I see.
One thing that's like very important to note is that like even though like your evaluations are defined over this binary like 0, 1, 0, 1, 0, 1 for everything, this polynomial can still be evaluated like everywhere else.
Because like their x is like binary, but like here r is not binary.
Not necessarily, yeah.
What's the stuff you underlined again on the right?
So this is like the row tensor product that Vitalik gives us in the blog post. He's like, okay, if you just take R3 and R4 and you do the tensor product, you get these 4 terms. And then the same thing happens for the columns. Like you have like the column terms are all going to share this guy, this guy, this guy, and this guy. Like R1, R2, R1, R2, R1, R2.
So it just so happens that the tensor product gives this.
Yeah.
So he's saying that the tensor product is the reason why we use this, but it's more certainly like once flattened it out and writing this, that's the reason these terms repeat itself.
Yeah.
What I'm trying to say is the tensor product is just an observation which one can make like once writing these terms.
Yeah.
terms of-
Exactly. It's like, well, it's the tensor product itself can be broken down into 2 halves,
Yeah.
where you're essentially doing a tensor product of tensor products, and that works really nicely. Like, yeah.
And this is only to make the commitment smaller?
This is essentially, this is a trick to essentially ensure that you're only communicating like root n sized information on each round.
Yeah, okay. So, like, when you prove evaluation, then what will happen? You're like, so, I mean, at some point, after commitment, you have to prove, and then verifier has to verify, like, from the same commitment scheme.
Yes. So, like, the reason you do this roughly is generally like this polynomial that you committed here. So this steps into like now back into ZK snark land. Like this polynomial is part of some sort of like arithmetization you've done, essentially. Like generally this usually encodes like all the elements of your witness. And you want to prove that all the elements of your witness satisfy some equation. Like in the R1CS case, it's this like A, B, C thing, right? So what you're doing and how you generally do that is like you evaluate this equation on a random point, completely random point. And if the equation is equal on both sides, then it's very likely that you do actually have a satisfying witness, even though you haven't revealed the whole thing. And this is because like the probability of two polynomials being equal at the exact same point at a random point is extremely small if they are different. That would mean they like there's a root essentially of
What's
the
the dilemma?
Schwarzschild polynomial. Yeah. Huh?
Degree of polynomial divided with the domain of the your domain.
Exactly. Yeah. So this explained
Is the entire block just like not telling the arithmetization part and then just taking into consideration that okay, you have done that, you have it in a hypercube.
Yeah.
Now how do you commute it basically?
Yeah, that's basically he like jumps to well, he's basically just describing a multilinear polynomial commitment scheme through the post. And he skips like a lot of the multilinear stuff. He's sort of just like, we're in a hypercube now, let's fucking
Yeah.
go. We're gonna make it a grid, let's fucking go. But yeah, that's what's going on here. And the progression of the post is like, this is just simple Binius. This is like kind of a useless thing because you can do way better than square root n if you're actually committing to polynomials. He then explains binary fields. Binary fields are really pretty and nice, like got a lot of good properties. And then the last section is essentially like showing how with this same setup, you can actually have all of these evaluations be binary, like inside. Like you can basically have your field be just F2. So everything, instead of 3, 1, 4, 1, it's like 0, 0, 1, 0, 1, 0, 1, 0, blah, 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 blah. And they do this really clever trick of, and this is where my intuition gets kind of fuzzy, but like they do this clever trick of like concatenating multiple columns together and treating them as if they were like one element, basically. And you need to do this to be able to expand your domain, so you can do this Reed-Solomon extension, and then you can do the rest of this procedure, basically. But yeah, why that works, he basically just says it's because binary fields are awesome. But I think it is possible to work through the math. Simple business. Any major questions?
Yes, I got a question. So
Yeah.
what is the purpose actually to raising the fact that there is like common factor between the different columns or the different rows?
What's the purpose of this?
Yeah, exactly.
Well, I guess it's just kind of how it is, I guess. Or it's a property of tensor products that essentially you can break it down into like
Isn't just because like there is like 4 columns and 4 is just the half of the number of bits you can have in each situation. Like you have like 4 digits which can be 0 or 1. So
Yeah.
yeah.
No, yeah, exactly. It's basically just like it just kind of happens as a result of like if you take these like square root n's, and this is kind of the confusing thing with 16 in particular is like log n, log 2 base n, and square root of n are the same. So it's confusing when what is being used or like how this scales to larger things. But roughly, like yeah, if you do like a square root n sized row tensor product and a square root n sized column tensor product, the tensor product of those things is going to be equal to like the full tensor product. I just said tensor product 6 times, but yeah, it's just a nice decomposition that we use to lower the amount of data that we're sending between the prover and the verifier. That's kind of the purpose, I guess,
Okay.
because we're looking for succinctness, and this isn't even
Yeah,
succinct.
okay.
This is like kind of succinct. And a lot of people would say this is like not a succinct argument, but they fixed that later. They kept cooking, and people will keep cooking, and this will become succinct within the next few months. So.
Okay, thank you.
Like how does the verification work like once creating the new tree query?
It's the Reed-Solomon thing that he was describing. Like you open up a bunch of random columns,
Yes.
and you prove that like the tensor product, or like sorry, the dot product of the row tensor product with this column is the same as the Reed-Solomon extension of the tensor product of the row tensor product of the like original set of wait, fuck. Oh my god. There's so many rows and columns and shit. Yeah, like essentially like you get to some like dot products here where you multiply the columns by the row tensor product, and you get to some like 4 digits here. If you Reed-Solomon extend that, the outputs there are going to be the same as Reed-Solomon extending these guys and
then
doing the same.
Same computation.
Exactly. And this is just a funny coincidence as well. Well, not coincidence. It's like He describes it nicely as just like when you do two linear operations, doesn't really matter if you order you two of them. They will both return the same thing. And we like abuse this to be able to test that like you've correctly read solved and extended each of these rows as you said you would. This is sort of thing that like only clicks like 60% the first time and you just kinda like hit it like a few more times and then you're like, okay, now I'm at 80% maybe. And then someone asks you a question, you're like, fuck, I'm actually at 40%. Like it's just, I don't know. If it doesn't fully click today, that's fine. But I hope this is better intuition for why we did all this tensor plotting business than the post gave.